So basically, the aim of excuse me, the aim of all this is to the aim of all this is to document my whole journey throughout my journey from as an engineering student, an undergrad to a math master. So in this lecture, in today's video, what we're going to do is we're going to go through a few problems of uh, real analysis in RUDIN's book, that is Principle of Mathematical Analysis. And what I'll be doing is I will be explaining the solutions to the best of my capacity. Excuse my throat. It's some sort of infection. So uh, let's begin. The first question that is I will share my screen. I hope it's visible. If not, it doesn't matter. It's mostly for personal usage only. So, okay. While the page loads, um, let me read out the first question. We're starting with numerical sequences and series diagrams. So the first question says that we have to prove that the convergence, so I'm writing this simultaneously, so I might be a bit slow. The convergence of Sn implies convergence of mod Sn. So we have to prove if it is true or not, and also look on whether it's true or not. Very nice. There is the let me put the number 22553. Okay, page number 79. Okay, as you can see, the first question. So the recurring theme in this shall be, uh, so as I would like to say, I am not really good real analysis expert. So I'll be reading solutions simultaneously and I will try to understand them and explain them to an imaginary audience. Thank you. Okay, so here we go. So Sn is our series. All right. So Sn is our sequence. That's it, not the series. So Sn is our sequence of numbers which can be real or either complex numbers. So we have to prove that the series Sn or the sequence Sn converges at some point. So as the solution states, let Sn be a sequence. And suppose Sn tends to S, that is the convergence point. Let's check that. So, right, and just a second. Yes. So, as I said, Sn converges to a point N. Oh, my bad, to a point S. So, right. So we use this uh, as an inequality, I'd say. So for all x and y belong to numbers or a real or imaginary, mod x minus mod y is always less than or equal to mod of x minus y, which is the triangle inequality. Right. So for any epsilon greater than zero, basically what the series uh, a sequence when it means that a sequence is converging is let's suppose Sn is a sequence which has n terms, right? So the sequence converges it meets to some point, right? For example, if Sn is 1 by n, let us just whiteboard, right? So F1 is our sequence. Uh, Sn is our sequence, and let's suppose that Sn is equal to 1 upon n. So this is our sequence. Uh, my bad. Right, this is our sequence. S1, S2, S3 are the numbers, and Sn is the nth term of our sequence. So what it means for a series to converge is, suppose as given in our example, Sn tends to 1 by n. Sn is equal to 1 by n. My apologies. So as Sn tends to infinity, n tends to infinity, Sn tends to 0. So if we had to formalize a definition of Sn converging to a point S, it would be that no matter any small distance, right, after the nth term, there is always a point on our sequence where all later terms stay at a certain small distance from that S. So formally, if we had to say that would be for some, so formal definition of our sequence conversion would be for any small distance For any small distance epsilon, let's say, mind you, I'm writing, so I might cause a little longer factor than time. So for any epsilon greater than zero, there exists an n which belongs to natural numbers such that uh, if n r small n is greater than n, Sn minus s is always less than epsilon, right? We want to get uh, so why we choose epsilon is we want to get exceptionally close to the smallest number as possible, which is again a subjective term. So for it, it's if you pick a small distance, like a small number like 0.1, there is also a smaller number than that, which is 0.001, and this can continue, right? So, which is why we choose an arbitrary value, which is epsilon, instead of getting to an exceptional close point. So, yeah, so coming back to our problem, yes, uh, right. We had to prove that the convergence of sequence Sn implies the convergence of uh, modulus of Sn as well. So, in order for us to prove that, we would have to take an arbitrary epsilon. Uh, So Sn tends to S, which means that for every uh, modulus Sn minus S is less than epsilon. Uh, so let us assume that Sn tends to S, right? So from that we want to show that modulus of Sn tends to modulus of S, which means since the absolute value function or the modulus function is continuous, uh, every xn term uh, right. So since our absolute value function is continuous, so every xn tends to x would imply that mod of xn will turn to x as well. Excuse me. So since Sn minus x is always less than the modulus of individuals of Sn minus s is always less than equal to mod of bracket Sn minus s. The- This is the triangle inequality. Uh, so if now that Sn minus s tends to 0, which follows that Sn minus s individual modes also tend to 0. Now, if you ask me that why does this tend to 0, then the distance between Sn minus s, which is epsilon, can be made any smallest of the positive number, which is a little bit greater than 0. So, which is equal to epsilon basically. If I had to write that, uh, so like Sn minus 10, Sn minus s tends to 0. Right. So what this means is 0, it's not exactly 0, it's just epsilon, which is the smallest possible number. Let me write this down. Greater than 0. Right. So this also implies since Sn minus s is equal to mod of mod Sn minus mod s. Since these two are equivalent, mod of Sn is somewhat similar to mod of s. Just, mod of similar tends to mod of s. Right. So yeah. So let's just so that we clear that why does it tend to 0? Why does it equal 0? Right. So if we prove that mod of Sn tends to s, so if Sn converges, this also implies that mod of Sn converges as well. Right. So if we had to prove the reverse, like the converse of that, we can do that via an example, I say. So, but uh, had we had to prove that mod Sn to Sn does it does the series converge? My bad. Let mod Sn mod of let mod of Sn tend to L. So if we choose an example, suppose let Sn be equal to minus 1 to the power n. So mod Sn would have to be 1 to the power n. So since mod Sn would always give us 1, whereas Sn would jump between minus 1 and 1, the converse is the false and it does not hold. Mod Sn is equal to, so first we have to write N is equal to minus 1 to the power n. Right, so mod Sn uh, is equal to n is equal to 1 to the power. Let me get it. So this is always 1 and this fluctuates between minus 1 and 1. Let me just type it out. Um, jumps between -1 -1 given to value of right. Uh, okay, so this the converse is not also. I think this should be it for the first question. Yes. So if we had to summarize that the convergence of sequence Sn implies the convergence of sequence S and mod. So uh, using triangle inequality, the individual mods is always the difference of individual mods is always less than greater to the difference of mods whole of individual. So using that analogy, we choose an epsilon which is greater than zero, but is a very arbitrarily small number, such that Sn minus S the whole of mod is always less than epsilon, right? Which is the formal definition of convergence. So using that, we had to that the convergence, and also for the converse, we used an example. We used a counter example which did not hold true. Moving on to the second question. Um, yes. So in this question, we have to calculate the limit of square root n to the power 2 plus n minus n. Right. Just for the, I'll try to paste it if I can here. Yeah. Line. Uh, Right. This is question. Right. So to calculate the limit of n square plus n whole root minus n. This will this be n tends to infinity, right? Let me specify that over here. Mhm. Right. Yeah. Uh, yeah. Okay. So let's do one thing. Let's just assume n is infinity. Let's just classical assumption, right? So let me just start out the question. Calculate limit. So as inside the square root, as n tends to infinity, n square plus n is almost similar to n as n is such a huge number. Since n tends to infinity, that means sorry. Since n tends to infinity, we can say that n square plus n is very similar to root of n square, which is almost as equal to n. So the expression which we get is n minus n, which is equal to 0. But since both n's are infinity, we cannot subtract it. So there's a trick. whenever we see a root of something minus 10 problem, what we do is we multiply the denominator and numerator by the conjugate. Right. So n square plus n minus n would be equal to rho n square plus n minus n square plus n upon n square plus n minus n. Right. Oh, plus n, my bad. So let me just uh, let's what I would do is e is equal to difficult to write it only using the laptop itself. So what we do is a minus n a plus n upon a plus n. I'm just exceed my life. I'm really sorry. Right. So this gives us from the LHS, it gives us n square plus n whole square minus of n square, which is um, so n square plus n whole square is the root and the square cancel themselves out. The denominator remains the same. So n square plus n minus n square upon root of n square plus n minus plus n. Right. This turns to n upon root of n square n plus n. So this uh, something that uh, was taught that is taught during, I think it was taught during engineering mathematics or sometimes. So this is a trick. So uh, during limits like the n tends to infinity n upon n square plus n root plus n, what we do is uh, we just take the highest power uh, and ignore all the other powers, right? So in the numerator, 1 is the highest power, and in the denominator, 2 is the highest power. So the limit just equals 1/2. You can also prove it by uh, you can prove it by canceling out n in the numerator and denominator. So like let's just see. So this gives us n upon n square plus l plus n. Right. So if we take n common, 1 upon uh, 1 upon 1 plus 1 by n plus 1. Now this tends to 0. And n tends to infinity, which gives us 1/2. That is our second problem. I think we would do one more problem, and then I think I would have to shut complete the video since I think there's a 40 minute time limit. So yeah, let let's just focus on our third problem for now. Mhm. Oh, another moving question. So we've been given that if n is equal to 1 is equal to root 2 and s n plus 1 is equal to root 2 plus root of Sn. Then we have to prove that Sn converges. Okay, so let's see. Yeah. Mm, yeah. Mm, if so we are given the sequence and we have to prove that Sn converges and that Sn2 for n, so we have to prove two things. Uh, right. So we have to prove first that Sn converges, and the second part that Sn is greater than 2. Right. So since uh, let's just prove the first part. So uh, since S1 is equal to root 2, which is 1.4, S2 is equal to root 2 plus root 2 inside root 2. Right. So uh, yeah. So if I had to, so let's just assume here we have improved this by contradiction. Let's assume S2 is greater than yeah, let's just assume that S2 is greater than 2, which means that root 2 plus root 2 inside the root is greater than 2. So squaring both sides. So 2 plus root 2 would be greater than 2. It is clearly false, right? Because root 2 is less than 2. Yeah. Uh, so for since proven for S3, Sn, so it also has to be true for Sn plus 1 by induction. So we can write that since Sn greater than 2, Sn plus 1 is also greater than 2. Right. And also, just a second. So, uh, for Sn to converge, I think Sn plus 1 should be Sn, Sn, right? Uh, just a second. Okay, I'll just write the question till the time S1 is equal to 2, 2, 0 to 2, S plus 1 is equal to root 2 plus root of Sn. So that's converted. Uh, in the conversion part, we have to do that the sequence is increasing and is bound above, right? So, for the base case, S1 is equal to root 2, which is equal to 1.4. Right. S2 would be root 2 plus root 2, which would be around 1.85, which is equal to S and A. Right. So, as we go up the sequence, S3, S4, S5, Sn, Sn plus 1 will always be less than 2. Uh, to show that it's increasing, uh, we want to prove Sn plus 1 is greater than equal to Sn. Root 2 plus root Sn is greater than equal to Sn. Just square both sides, right? 2 plus root Sn is greater than equal to Sn square. Mm, yeah. So this is um, how do I explain this? So Sn is positive and Sn square is also positive, right? Uh, so this inequality, that is 2 plus root of Sn is greater than equal to Sn square, holds true when Sn is equal to Sn belongs to 2, root 2 comma 2. Right. Uh, so indeed, Sn is Sn plus 1 is increasing. I think this is it. To summarize the solution, is uh, we have to prove that Sn converges and also prove that uh, Sn is always present. Okay, so the first one, what we did was for Sn to converge, for Sn to converge, there has to be two things that uh, it needs to satisfy. For a sequence to converge, two things to be satisfied and should be bounded above, and it should be the sequence should be increasing. So we have proof that sequence is increasing. Also, we have proof that the sequence is bounded above its state. So according to the monotone convergence theorem, we have proved that Fn converges. Also, for part 2, which is Fn is less than 2, it's very straightforward. We just square both the sides and yeah, we get our answer. That is it. Thank you.